we're today with Chris Turner and the Apziva community. So we're welcoming you all to a fascinating session, an Apziva workshop. My name is Timmy. I'm the Director of AI at Apziva. We're very pleased to have you with us today. Today we have Chris Turner with us. Chris is an AI expert and also an AI resident at Apziva. A background in genetics and biology, with years of experience in geospatial data science as well. So, Chris, welcome on board. We have our speaker, Chris Turner, with us. Stage is yours. Could you please briefly tell us a little bit about yourself and also what are you going to be talking about today?
Yeah, sure. So my name is Chris Turner, and I kind of began my journey in analytical thinking at UC Berkeley. I studied genetics and plant biology there, and then I briefly worked at the United States Department of Agriculture and the Plant Gene Expression Center on a functional genetics project in the lab, where I discovered how much I loved being in school and learning new things every day, and how much I didn't love as much working in the lab and doing the same thing every day. I worked in some different capacities after that, and then I eventually found my way into a series of internships in South America, working for a few different conservation organizations around GIS, which is Geographic Information Systems, and then a few projects related to remote sensing. And it was through those projects I became more aware of computer vision models. And I eventually found my way into a project in the Madre de Dios region in southern Peru, where I built a computer vision model to segment out castagna trees, you might know them as Brazil nut trees, from drone images. And it was there that I came in contact with a different NGO that I'm actually currently working on a project now where we are detecting the fruits of Brazil nut trees from drone images, with the goal of connecting those detections to harvest data so that we can predict harvest volume from drone flights. So it was through that experience with computer vision I became more aware of AI and machine learning, and eventually found Apziva on LinkedIn, and I applied and got in. And that is kind of what led me here today to this talk about fine-tuning Hugging Face large language models with QLoRA. So let's see. Where is the share screen? Oh, there it is. Share screen presentation. Okay. Are we seeing the presentation screen here?
Mm-hmm.
Okay. And is it full screen or no?
It's full screen.
Okay. Excellent. Okay. So we've all used these different large language models like ChatGPT and Grok and others, and they're truly amazing. Yes.
There's a like pop-up for me. I don't know, maybe
Oh, there we go. How's that?
Yeah, that's perfect.
Okay. So we've all used these large language models that we've heard of, like ChatGPT, and they're truly amazing. They can answer almost anything you throw at them. There's just these like amazing general purpose models. And so one of the things that I've become aware of at working with Apziva is that we have access to these other open source models from repositories like Hugging Face and other places. And we can actually train these open source models to outperform ChatGPT on a very specific task or a very specific domain. And so that was kind of a surprise to me. Um, and so, traditional fine tuning of these large language models takes a ton of GPU power, a ton of time. Sometimes they train for days or up to a week to get a model like ChatGPT running. And so that something like that is just really not possible on our home computers. Even with these large language models that are much smaller, we're still dealing with a model that has parameters of like billions of parameters or tens of billions of parameters. And so this is where the idea of parameter efficient tuning has come in. It's better known as PEFT. And so there's a bunch of different kinds of PEFT, but the two most popular are called LoRa, which is low rank adapters, and QLoRA, which stands for quantized low rank adapters. And with these processes, it makes it possible for us to fine tune these models on our home machines. So first, I want you to imagine that there's a company and that they want to build an app, and they want to use different types of models for their application. And so, they have a specific translation function that they want to have, a specific summarization function, math that is specific to their business or company, and then like a specific accounting function. So one way they could design their app is to have a different large language model for each of these functions. And if you designed it like this, you would get really good performance for each of these functions. But the problem would be that each of these models takes a lot of storage. They take a lot of compute power. You would have to have a tuning pipeline for every one of these models. So as the model grows, it would just be kind of a nightmare to maintain and store and keep going. Another way you can handle this is to have one giant model that would do all of the tasks, and this would be much easier to host, much easier to track, much easier to update. But the trade-off here would be for performance. The performance would suffer a little bit on all of the tasks. And then as you kept adding more tasks, the performance on all of the tasks would begin to degrade a little bit. And so this is where parameter efficient tuning really shines. So with parameter efficient tuning, we have a base model, and we kind of freeze the base model in place. And then we train these smaller LoRa adapters for specific cases that we need. And so these LoRa adapters are much smaller. They're lightweight. They're easy to store. You can swap them in and out on demand and use them with the base model, and then you can complete the task that you want to do. And so we can train these without massive compute power, and the setup and administration is just much easier. And so with this design, you get the flexibility of specialized models with these LoRa adapters, but you get the efficiency of like a shared backbone of the base model here. So it's really a nice innovation. So just to understand what these LoRa adapters are doing, I'm going to introduce a very simple neural network. This neural network has two input neurons. The first hidden layer has 3 neurons. The second hidden layer has 4 neurons, and then it's going to have 2 output layers, 2 output neurons in the output layer. Okay, and so when we are using LoRa adapters, what we're actually going to do is insert these LoRa adapters in between these hidden layers here in the model. And we'll talk a little bit about how that works. But before we do that, I just want to introduce a little bit of how fine tuning works so that we can really appreciate what the LoRa adapters are doing. And so to understand fine tuning, we have to know what a weight matrix is. And so here we have a first hidden layer, and I've labeled the neurons in the hidden layer here, X1, X2, and X3. And then we have the second hidden layer in the forward position from that layer, and it has 4 neurons, and I'm labeled them Y1 through Y4. And we can see that there is a connection between this neuron and every neuron in the forward layer. And that's true for every neuron here in this first hidden layer. And so with each of these connections comes what's called a weight, which is just a floating point value. And each of these connections has a weight associated with it. And so these weights are also referred to as parameters. And these floating point values are what the network is learning when we are doing fine training. They're being adjusted in subtle ways such that the output will be better and better. And so these weights are stored in what's called a weight matrix. And you can see there's as many weights in this weight matrix as there is connections between these two layers. And the weight matrix is usually denoted with the capital W. And here I just wanted to kind of reiterate that the weight matrix is actually just floating point numbers. So this is just an example of like a real weight matrix which is just a data structure holding these floating point numbers. And so in traditional fine tuning, values will enter the input neurons. There will be some kind of calculations. They will land here in the next layer. There will be more calculations. Then new numbers will land here in this layer. They will do more calculations, and we'll finally get some output numbers here in the output layer. So what are those calculations, and how are they deciding what the values are? And so if we're going to try to calculate the value for this neuron Y1, which we're going to label Z, it's actually quite a simple calculation. It's called a weighted sum. And here we're going to take the value of X1, multiply it times the weight of that connection, plus the value of X2, multiply it times the weight of that connection, and then the same for the value of X3, multiply it times the weight of that connection. Now there's actually another parameter here called a bias. I'm just setting the bias here equal to 0 for simplicity. And so you do this weighted sum calculation and you add a bias to get the value here for Z. So if we run that forward with these numbers and these weights, we get a value of 2.8 for this neuron. And then we're just going to repeat that process for all of these neurons, and then we'll move forward to the next layer and we'll repeat that process until we get to the end and we get some output values. So after a number lands in a neuron, it actually goes through what's called an activation. And the activation function, its job is just to squish whatever number lands in there to be between -1 and 1. And so there's actually a bunch of different kinds of activation functions, but I just chose one for an example. This one's called tan H. It's calculated like this, and so if we took the tan H of 2.8, it would be 0.992, which is indeed between -1 and 1. So that calculation happens for every number that lands into a neuron. Once the numbers reach the output layer, we have the result of this forward pass of the network. So in this example, we have a result here for this neuron is 0.1, and we have a result for this neuron here, which is 0.5. And so now we need to calculate the loss or the error of this run of the network. And so to do that, we're going to compare the values of the output to the known ground truth values of this data. So here 0.1 is pretty close to 0, and 0.5 is not so close to 1. And so just like in activations with the loss error functions, there's a bunch of different loss error functions you can use. And I just chose cross entropy loss for an example. It's calculated like this. I don't really have time to go through all of that, but it's really just a measure of how good the output of the network is compared to what we know the answer should be. And so here we're getting the total loss, which is kind of like the average of both of the losses for this neuron and this neuron. And so we add those together, divide by 2, and we come up with a loss error of 0.39925 for this forward pass in the network. So In fine tuning, we need to use this loss to adjust those weights so that they will reduce the loss next time. So how do we do that? And we do that with something called backpropagation. And this is where the error signal that we just calculated propagates back through the network. And so here I've just drawn one arrow, but in reality, the backpropagation is going to filter back through every single connection in the network for every single layer until it gets back to the input neurons. And so how does it know which way to adjust these weights for each of the connections? And that's by using an algorithm called gradient descent. And so gradient descent is it uses a little bit of tricky calculus, and so this could be a whole talk in itself. I don't really have time to like explain the whole calculus behind everything, but here we're taking the slope of the loss with respect to weight, and it's giving us an idea of which direction we need to change each of these weights so that the next time we run data through this network, the loss will be decreased. And so we need to do that for each of these connections, of course. And so we keep running through that process, and we keep changing the weights until the outputs of the network get closer and closer to what we know the ground truth should be. And so if you're doing full fine tuning, when we do this back propagation with gradient descent, we actually create what's called a change in W, or a delta W. And so it's a separate data structure of weights, and it's just a data structure that is saying this is how much we want to change the original weights by. So if we had our old weight matrix here for these connections, we would get a delta W for these connections, and then we would add them together, and now we have our new weight matrix that we're going to use on the next pass in the network. And so that's a little bit of background about how the fine tuning works. And so now we can talk a little bit about how the LoRa adapters are going to help us in this process, and how does adding something new to the model make things easier and simpler. And so part of the answer to that is that when we add these LoRa adapters to the model, the weights, the original weight matrix for the connections between the layers in the model are actually frozen in place. And we're not going to be adjusting all of those weights with backpropagation anymore. We're going to be adjusting only the weights in these LoRa adapters. And so let's take a little closer look at what that means. So there's actually two different LoRa adapters that will be inserted, and they are generally labeled as A and B. And when you're working with LoRa, you have to call out what's called a rank. It's denoted by lowercase r here. And so for this example, I just made a rank of 2. And to calculate the size of the matrix A for the LoRa adapter, we take the number of rows and multiply it times rank, which is 8. And you can see we have 8 weights here in this LoRa adapter. And then to calculate the size of B, we take the rank times the number of columns, which is 6. And you can see we have 6 weights here in this LoRa adapter. And so how is this really helping us get the change in W, or what we should change the weights to? And the answer to that is through the magic of matrix multiplication. So here's the empirical formula of how this works. If we have these two matrices and we train them, we adjust the weights only in these small matrices, and then we multiply this times this one plus this times this one, which is denoted here, we can follow that math across both matrices, and we can recreate a low rank adaptation of what the change in W would be. It's called a low rank adaptation, I believe. It's really just like an estimate of what the change in W would have been if we had followed full fine tuning and use gradient descent to update every model weight in every connection of the model. So basically, we can just use these smaller LoRa adapters, do some matrix multiplication, and get back the original change in W or something really close to it that will be a great representation of what would have happened if we used full fine tuning. And so sometimes when I see empirical data or notation, my brain kind of turns off. And so I just wanted to include this slide of actual numbers. So here's a LoRa adapter with some floating point values for weights in it. Here's the LoRa adapter B. You can follow the simple multiplication here, and then we will come up with the product of A times B, which is the delta W, or the change in W that we can use to update the weight matrix when training is done. And so how do we do that update? So here we have an old weight matrix, the weight matrix, the original weight matrix, maybe I should say, of the model. We trained our LoRa adapters. We have our new values for them, and we did the multiplication of A times B, and then we add those together, and we get the new weight matrix of the entire model without having to have trained all of the weights in the entire model. So it's pretty neat. So just to give you an example of the kind of savings, because you can really only see the savings when you scale up to a really large model. If you had a weight matrix or a layer in a model that had 4,096 neurons, and the forward layer between it had 4,096 neurons, you would have 16.7 million connections, or 16.7 million parameters that you would need to train in full fine tuning. If you used LoRa adapters instead and inserted those, and we chose a rank of 4, for example, then the LoRa adapter A would have 16,384 parameters, and likewise the LoRa adapter B would have 16,384. And so if we're only training the LoRa adapters, then there's only 32,768 adapters, or just 0.2% of the original amount of parameters in the base model. So if you want to full fine tune this layer, you got to do backpropagation and gradient descent 16.7 million times. If you want to do that with the LoRa adapters, we only have to do it 32,768 times. And so you can really see here how using this LoRa trick is really making it so much easier for our tiny machines at home to train one of these giant models. And so that's really like the main trick that LoRa uses to help us train these models. But what is it that puts the Q in QLoRA? And that is quantization. So quantization is just a way of changing high precision numbers to a more low precision format. It cuts the memory use of the computer drastically, and it speeds up calculations. So here's just one example. If we had 17.5 and we wanted to quantize it to whole numbers, it would get quantized into 17. And if we wanted to quantize that into tens, this number would get quantized into the number 10. And then likewise for these examples as well. And so that's basically what quantization is. Every time you quantize a number, you're reducing the amount of space you need in the computer to hold that value. And so speaking about space in the computer, I just pulled this slide from the Hugging Face website. And I wanted to just illustrate that if we started with a floating point 32 number, it would have a lot of significant digits, but we need 32 binary spaces in the computer to hold that number. And so these numbers are held in this fashion here, and they have these 3 different parts: the mantissa, the exponent, and the sign. And there's a little bit of the calculation that the computer needs to do to get the floating point number out of this when your program is going to use it. But I just wanted to point out that a floating point 32 takes 32 binary spaces. And if we're going to reduce a floating point 32 and quantize it down to a floating point 16, it's going to take half of the size. And if we quantize the floating point 32 down to a floating point 8 number, it would take 25% of the size. So we can really see the computer space that we're saving here by quantizing these numbers down to smaller formats. We are, however, losing some significant digits on the number. But the makers of LoRa and QLoRA did not stop there at floating point 8. They actually designed their own float structure called the 4-bit normal float. And so the 4-bit normal float doesn't have the 3 parts that was shown on that slide previously. It has a sign and what's called a value code. And so you can imagine if we're starting with floating point 32 numbers in a model on Hugging Face, and we're downloading it onto our machine, and by the time it lands on our machine, it's in 4-bit normal float, we're saving a ton of space. And if you're talking about 50 billion parameter model, this makes a huge difference on how much parameters you can fit in your model and still be doing calculations and other things. And so the question becomes, how do we turn this normal 4-bit float here with a sign and a value code into an actual value that's a floating point number that we can use in calculations? And so the way that they did that was building what they called a map. They kind of hard-coded this map into the QLoRA program. And so with a value code, you have 3 bits here, and there are 8 different ways that you can organize ones and zeros or binary code in these 3 bits. And since we have a sign value that can be 0 or 1, that means there are 16 different combinations that we could make here. And so, for example, if we had a 4-bit normal float that had a sign of 0 and a value code of 100, then it would be mapped here to this value of plus 0.35. And then if it had a value of 1 and it had the same value code of 100, then it would have a value of negative 0.353. So the value codes here are the value codes here are kind of hard coded into the float value, and so to get a better idea of how they decided what those hard-coded values are going to be, we need to understand that the weight matrix here has a a normal curve to it. So most of the values in a weight matrix are actually falling around 0. And as you step out here closer to 1 or -1 or 1, there are less and less values in the weight matrix that will be in those ranges. So let's see here. So if we designed that map, that value code map for the normal 4-bit float, and had the numbers mapped to like evenly distributed places, then what would happen is that most of the values would get turned into these two buckets here. And what would happen is you would kind of lose the resolution or the relationships between most of your weights, because most of the weights here are actually really close to 0. So I'm having trouble resizing this thing for some reason. Anyway, so what the makers of LoRa and QLoRA did was designed a non-linear mapping structure. And they made the buckets that these values would fall into a lot smaller around the 0 range. And then as you step closer to -1 or closer to 1, they made the buckets bigger and bigger. And so designing the value code map for the normal 4-bit float like this helps to keep the relationships between all of the parameters, especially the ones that are really close to zero, keeps those relationships intact, and it keeps the kind of inherent intelligence of the model's parameters like intact, even as they're being changed into this normal 4-bit structure from where we're downloading it. And so how does this actually work in practice? So when we're downloading from Hugging Face, you know, this model here in this example is starting in floating point 16, and the program will go and download this thing in blocks. One of the typical block sizes is blocks of 64. And so if we had 64 weights, that's represented here by this block of 8 by 8, and we downloaded that in float 16, it would be 128 bytes space on our computer. But if we convert it into the 4-bit normal float, that 128 bytes is now going to only take 32 bytes. And so for each of these blocks, there's an additional calculation that goes on, and we have to create these what are called quantization constants. And so one of the quantization constants is scale, and the scale is just a measure of like what is the biggest number in this block and what is the smallest number in this block. And then it creates another constant called the 0 point, and that is what is the sort of middle of the largest and the smallest value within this specific block. And so the quantization constants are actually created in floating point 32. And so those take 4 bytes each. And so you can imagine that 4 bytes may not seem like much, but if you're downloading a 50 billion parameter model and you're only doing it in chunks of 64 weights at a time, I don't know how many chunks of 64 are in 50 billion, but there's a lot. So holding the scale and the 0 point at floating point 32 values is actually going to take up a lot of space as well. So the inventors of QLoRA instituted double quantization, and why that sounds maybe a little bit complicated, it's actually just the quantization of those quantization constants. And so here we've already downloaded this onto our machine. It's in all of the weights here that we downloaded are now in the 4-bit normal float. It's only taking 32 bytes, and we're taking these scale and the 0 point value for this block, and we are going to quantize them down into floating point 16, so they're going to be half the size. And so that's an additional measure that they took to help crunch this model down and compress it down so that we can fit it onto our computer and begin to train it for our own purposes. And so I just wanted to give you a better idea of what this storage is. If we had a floating point 32 model and we downloaded it in floating point 32 onto our machine, it would be 100% of the size. It would be the same size. If we quantize that model into a floating point 16, it would just take up 15% of the size. And then if we quantized that floating point 32 model all the way down to the 4-bit normal float, it would take 15.6% of the size. And then if we went the extra step of doing double quantization, we quantized the quantization constants, it would only be 14.1% of the original size of the model that we downloaded from Hugging Face. So it's a really big help in helping us get these models onto our machine in a form that our smaller machines can crunch and do the numbers that we want to accomplish. And so that's not the only thing that the makers of QLoRA instituted to make this easier. They also instituted what are called paged optimizers. And so this really starts to get into some deeper stuff about computer hardware and how the computer works on a very low level. So this is not my area of expertise here, but I can give a basic explanation of what's going on here. So the computer issues out what are called pages. And when a program needs memory to do something, it will get a page of memory and it will start filling up that page of memory. And so your computer is broken into two different parts. There's the GPU and the CPU. The GPU is really good at doing parallel calculations. It can do a ton of calculations at once, and the CPU has a ton of RAM in it, and it can store a lot of information. And so the paged optimizers is really just a way of making sure that any of the data that's needed for calculations, this page of memory will be moved onto the GPU, and any data that's not needed for calculations will be moved to the CPU and for storage. So it's kind of like a smart paged memory function that just juggles the memory pages of data of all of our weights around the computer for us. And so now I thought we would just kind of jump into a little bit of the code and kind of see how we could use this in practice. And so this is just kind of a basic version of what you would do if you want to use PEFT on your machine. So here we're uploading the torch package, and here we're uploading the PREFT for parameter efficient fine tuning. And here is the transformers model from Hugging Face, and we're going to use the bits and bytes config to get this model from Hugging Face onto our machine. And so here I'm just downloading the GPT NEOX 20 billion parameter model, and then we need to create the bits and bytes config. And so this is going to tell the program what form do we want this to be when it lands on our machine. And so we're going to pass some arguments here to the bits and bytes config. We're going to tell it that yes, we want to load this model onto our machine in 4-bit normal float, true. We're going to use double quantization, so we want to go ahead and quantize those quantization constants. The 4-bit type that we're going to use is the 4-bit normal float that I mentioned earlier that they invented for this process. And then there's going to be a compute type. And so the LoRa adapters that we insert to the model, they're going to actually be in floating point 16 form. They're not going to be in the 4-bit normal float form. And so this is just calling out how many significant digits or what kind of floating point number are we going to have in our LoRa adapters. And so here we're going to get the model reference to the model on our machine, and we're going to use the from prechain function here. We're going to pass in the model that we're starting with, this base model, and we're going to pass in the config that we just created. And then we have here the device map, and I believe this is just stating where on the machine this model is going to land, and I believe this is telling it to land in the first spot of the GPU. I'm pretty sure that that's correct. And so now we have this model on our machine. We've taken this model from Hugging Face and we've quantized it into this 4-bit normal float structure. And now we have it on our machine, but we haven't yet put in these LoRa adapters that we're going to train. And so to do that, we first need to use this prepare model for k-bit training function. And what this is doing is freezing the base weights of the model. And it's, I kind of think of it like cutting the connections of the model as it was built. And it's getting the model ready to insert these LoRa adapters, okay? And then we need to create a LoRa config. And so this is going to spell out what our LoRa adapters are going to look like. And so here is the rank, which we spoke about earlier. It's denoted by a little r. Ranks control the size of those LoRa adapters, A and B, that we spoke about. And so ranks can be anywhere from I think 1 to 20 or so. It kind of depends on how many parameters are in the base model that you're using. The smaller the rank, the smaller the LoRa adapters will be and the less calculations your machine will need to do. but the less accurate the low rank estimation of your change in weights will be. So bigger R, bigger adapters, a better low rank estimation. Okay. And then we have the LoRa alpha. This is kind of controlling how strong the influence of the LoRa adapters will be once we are updating the model's parameters with these trained LoRa adapters. So the bigger the LoRa alpha, the bigger the influence of these trained adapters will have on the final result of the network. Here we have target modules. So this is allowing us to put these LoRa adapters in different layers of the model. And you pass different strings here to put them in different layers. You can pass multiple different strings into this Python list and insert these adapters in different places. And I think the strings can be kind of different depending on what model you choose. So you might need to look up the documentation of the model to know where you're inserting these adapters and or where you want to insert them, or if you want to insert them everywhere, or whatever you want to do. Here we have LoRa dropout. So dropout is just randomly turning off different neurons in the LoRa adapters. Here I've set it to 0.05, so I think we'd be turning off randomly 5% of the neurons in any forward pass. And this helps to prevent the model from overfitting to your data. And because LoRa adapters can tend to overfit to data sometimes. So adding some dropout can help it to not overfit. Here we're setting the bias to none. So if you remember from the weighted calculations that we did in the forward pass, there was a bias value that gets added on the end. And here I've set it to none. So I assume this would set all of the bias values to 0. And then we set the task type. The base model that I downloaded was just a language model. And so we would set this task type to casual language model. And so now we have our config and we have our model that's prepared for K-bit training. And we can use the get_peft model function, pass it in our model and our config, and we're going to get back a model that has the LoRa adapters. So now we have downloaded this model from Hugging Face. We have quantized all of the model's parameters into the 4-bit normal float structure, and we have now inserted these LoRa adapters into the model. And so how do we do some fine tuning with this on our custom data? So here I just downloaded a English quotes library here into this data set. Here, we're just getting the PEFT model again, so we're inserting the LoRa adapters. We're getting a tokenizer for that model, and this is a tokenizer function that's going to tokenize our complete data set. So we get our tokenized data set here by mapping the data set of English quotes to this function, and it returns the tokenized version of that data set. And then we're going to create a series of training arguments here for the trainer. So we're going to use the training arguments function, and we're going to set an output directory to put our results. We can set a batch size. So you can set the batch size to whatever you want. If you set it to a lower setting, it will take it longer to train. And you can do that if you're kind of running to the edge of your machine's abilities. You can set the batch size a little bit lower, and then it will help you get through the training process, but it's going to take a bit longer. The gradient accumulation steps, this is still a bit abstract to me, and I'm not really comfortable talking about what the gradient accumulation steps means. So afterwards, if somebody, after the talk here, if somebody out there has a better idea of what this means, we can maybe talk about it in the discussion. The number of training epochs here. So this is just referring to how many times are we going to go forward through the network, get the error and loss, do back propagation with gradient descent, and adjust the parameters so that they reduce the loss just a little bit. And so right now it's set to 3. That's very low. If you're going to fully fine tune some LoRa adapters or fine tune in the regular way, you're going to fine tune the whole model, you'd probably use more epochs than that. But if you're just testing, you can start with like a low number and make sure that everything's running correctly. And then logging steps. So this controls how often, you know, it's going to log data to you to the console while it's doing its training. And then we have save strategy epoch. So this is going to save all of the data and metadata for every epoch of training. If you set this to epoch, you can set this to different values. So maybe you want it to only save the training for every 5 epochs or 10 epochs, and that can help you if you're running out of memory and space on your computer. The learning rate. So here the learning rate is set to 0.0002. And so, you know, we use the gradient descent to decide in which direction, up or down, and are we going to change these weights so that the loss is reduced. But the learning rate controls like how big of a step in that direction are we going to go. So if your learning rate is too big, you can kind of overshoot the path, the quickest path to the best weight, and so if your model is showing like strange results in the training graphs, you can reduce the learning rate, and it will take smaller steps down the gradient such that it kind of stays on the right path until it comes down to a more correct answer. And then FP16, this just has to do with the fact that there is there's mixed floating point numbers in here. We have LoRa adapters that are floating point 16, and then we have the weights of the model that are held in 4-bit normal float. And so when it's going to need to do calculations between those two, this is just helping the trainer to know that you're going to have to deal with these mixed calculations. And so we can get a trainer variable by using the trainer function. We pass it the model that we created. We pass it our training arguments. And then we're going to pass it our training data set from the tokenized version that we created. So here we have that with the tokenized train section here. And then we call trainer.train. And now we are training our English quotes data set on a model that we downloaded from Hugging Face, quantized in 4-bit normal float, inserted LoRa adapters, and now we are finally training our new network, our new LoRa adapters. And so in terms of using the LoRa adapters, there's 2 different ways that you can use them for inference on a model. The first way you can do it is kind of back to one of those first slides that I showed you that had the base model with the LoRa adapter on top of it. And so here we're using the LoRa adapter and the base model together. And so here we have a base model, and here we have our already fine-tuned adapter. We're going to get a tokenizer from our base model here, and then we are going to put those 2 together. So here we're getting our model from pre-trained LoRa adapters and a base model, and here we have the base model and the LoRa adapters working together. And then we load those adapters, and then we create an inputs variable. Here we're just passing to the model, hello, how are you? And then we're going to tokenize that into tokens so that the model can do its magic. And then we're going to get our outputs by using the model and the generate function and passing it our inputs. And then we can print the tokenized version of the outputs for the response from the model. So here we use the adapters and the model together, and we got a response from the model. We can also take the values in the trained adapters and merge those values back into the model, and then we can remove the LoRa adapters and then just do inference on the model with changed values of the base model. And so here we're changing those values with the merge and unload function, and we will get our model now. We will get a tokenizer from our model, and then we follow the same path here. We get our inputs, hello, how are you? We pass those inputs with the generate function to get our tokenized outputs, and then we tokenize the outputs variable to get the human readable version or the answer or response from the model that we have merged our adapters into. And so, there are some areas here where QLoRA can fall short. It works best for tasks where the base model already has some idea of what's going on. So it can be kind of hard to use QLoRA if you're trying to teach the model something completely new that it doesn't know. LoRa can overfit to small data sets. So that's one problem you could face depending on how much data you have. LoRa and QLoRa tend to work best with text. It doesn't work or seem to work as well yet with audio or images or like cross-modal tasks. So if you want it to go text to audio or text to image or text to video or something like that, QLoRA is probably going to struggle. It's weak on unsupported languages, which makes sense because it needs to have, the base model needs to have some kind of idea of what it's doing. So here you would be trying to teach it completely new tasks. So if you're struggling with your LoRa or QLoRA project, one thing you could try to do is to download the model from Hugging Face, but maybe not download it all the way to the 4-bit normal float that they created. You could try downloading it to like an 8-bit format, and as long as it still fits on your computer, you would have some extra significant digits in your weights, and perhaps that could increase the performance of your model. And then also you can kind of juggle around or change or add these LoRa adapters between different layers of your model. So if you remember the target modules argument that we were passing to one of the functions there for the LoRa config, you can kind of add more of these LoRa adapters or add them only to specific layers in your model and see if that kind of changes the performance of the model and what you're trying to do. So basically, QLoRA helps us download these models into a 4-bit format on our computer. It institutes double quantization, which helps compress the data even further. They instituted the paged optimizers, which help our tiny computers deal with these giant amounts of data. In addition, we're assisted by the process of LoRa, where we only need to train these smaller LoRa adapters instead of training every weight in the original base model. And so with this process, depending on your computer size, of course, we can train models, 50, 60, maybe 70 billion parameters on a single GPU, which is, really amazing that we can do that. It reduces the compute cost for the small guy like us. It reduces the energy cost, and it really opens up the world of large language models and fine tuning to anyone. And it kind of democratizes the process, and it pulls some of the power away from big tech being the only people that could afford to train a model and for any kind of specific task. So it's really kind of an amazing process that they designed to make this work. And it was really kind of fun doing a deep dive and kind of figuring out how this whole process worked. And so, yeah, I appreciate you guys coming to listen today, and yeah, if you have any questions, I'd be happy to try to do my best to answer them.
We do have a few questions. Chris, thank you so much to begin with.
Yes.
This was breathtaking, to be
Oh,
honest.
thank you. Thank you.
Thank you so much for the talk. Very informative, packed with full of insights. Um, there are a few questions, but there was somebody raising hands. I think Nazar Kamal. Kamal.
Yeah, so because I didn't know whether should we
Yeah,
speak our question or should I type, so I was in the middle of typing the
go
question.
ahead. Go ahead. But we have
So my
multiple questions, so go ahead. We
Yeah,
can.
so my question like can be split into two parts. So first one is this the standard to use only two LoRa adapters, like the matrices for LoRa adapters? And if not, and we can use multiple adapters, so what will be the strategy of placing them, like in between how many layers should we place one LoRa adapters? If this question makes sense.
Yes. So the first question is it always two adapters? And I believe the answer to that would be yes, because we have to go through that process of matrix multiplication, and we have to come up with a result of a weight matrix or a delta matrix that would be the same size as the weight matrix of the connections. So that's where we went through the process of creating LoRa adapter A and B, and we do that multiplication of A and B, and it creates the same exact size matrix as the weight matrix of the original original base model. So yes to that. As far as the different layers, yes, I think that there is a difference depending on what types of layers you insert these adapters into. You can get kind of a big difference. So I'm not really sure I could go deep enough to explain to you, which types of layers are the best to insert adapters. But yes, there
You
is
you
there is a
can
big
go ahead.
difference.
You can go ahead because I am a master's in data science student and I'm in my final year and I'm working on my thesis project which involves like NLP for the Arabic language. So I am going for the text from like so it will be emotion detection from speech and sentiment analysis from text, and I am in the way of figuring out how to diffuse both the models together and get the best output, because I cannot use any pre-trained model because this is the academic setting. So I have to do everything on my own, like building my own models and later on comparing with any pre-trained model or something. So I am quite familiar with all the terminologies and all. I have read few research papers which are using LoRa and QLoRA. I have not tried it myself. So this was my chance to get a deep dive, like a kind of a hands-on presentation before I try it myself.
Yeah. So I mean, it sounds like you might be able to help me a little bit here. In terms of where we would the strategy of where you would insert these LoRa adapters. And so I don't know if anybody else out there has anything to add here. I'm not really I don't really know the answer to your question.
Yeah, it's okay, it's fine. Thank you.
Yeah.
I think we have Federico. Federico has a question. Federico, go ahead, please.
Hello, hi everyone.
Hi.
So first of all, Chris, congratulations for your presentation. Very insightful, very
Thank you.
interesting topic. So we understood that there's a big gain in terms of space, in memory, and disk also to work with those huge models. But do you know, in terms of performance, which is the cost of using QLoRA in the different modes?
Yes.
Okay.
I have a basic idea, and actually, you know, it's probably something I should have included on one of the slides here. But I kind of ran across a few numbers when I was researching all this, and you know, you can get it was really surprising to me that you could do all of this quantization, and you could, you know, take these floating point 32 values down to 4 bits and just map them to these basic numbers here, and you know, you don't really lose that much in performance. You know, I think somewhere I read you know, for the same task on a large model, you could get like 96% of the performance. I'm not sure exactly, you know, exactly what that means, but you know, you can get really high performance from a model that's been quantized down in this way, and that's quite surprising because, you know, floating point 32 is a pretty big it's a number with, you know, a lot of significant digits, and so the fact that you know, we go through all this trouble to train these giant models, and they have all of these significant digits on all of the weights, and then we can just like chop it all off like this and then still have the model spit out answers that make sense is really kind of fascinating. In general, on the same task that you might be feeding to Chat GPT or something like that, you know, you can get really high outputs, and then if you're talking about a very domain specific task that like wasn't included in something like the base model's training, you can actually get better results with one of these models, as long as you have enough training data and you've set everything up right.
Wow.
The loss in performance is kind of minimal, especially compared to like how much we've altered the model from its original state. So yeah, it's truly impressive what they designed.
Wow, very interesting. It makes me makes it even more interesting. So wow, I'm shocked, and very interesting topic. Thank you for your presentation.
Yeah, thank you.
We do have another question from Chukwuma. Can you use this method for RAG systems?
Yes, actually, I believe you can. You can use retrieval augmented generation, I believe it's called, in conjunction with this, and so it's actually something you can use if you have a small data set and you're you know, overfitting to your data. You can use that and pull in some new data for yourself and see if that helps to train your model a little better. So yeah, I believe the answer is yes.
Cool. Chris, your talk was quite informative. Thank you so much once again. I have a question.
Okay.
Have you, in what setup you used, or have you used fine-tuning and LoRa and QLoRA?
So I used it on one of our projects here at Apziva for the ranking of candidates, and so, you know, I was you know, having trouble training some of these models, or getting a regular model to work in Google Colab, and so you suggested using QLoRA to see if I could get a slightly bigger model, but you know, get some better results, because I could only download these really small compact models and get them to work in Colab. And so with this process, I was able to get a little bit better results by using a sort of medium-sized model and attacking the candidates problem candidate ranking problem with a quantized medium size model. So yeah, it worked. It works for me.
Awesome. Awesome.
Yeah.
I mean, like I already knew the answer, but like it could be really inspiring for others in the community
Yeah.
to how to like use these type of like methods to solve real practical problems. Thank you so much.
Yeah. You're welcome.
It was great. Thank you so much. And like it was a great session. Thank you guys for joining. So like I know you do have like more questions. Maybe like you can reach out to Chris Turner. He from LinkedIn. He'd be happy to answer anything you're curious about on the topic. Sure. But I believe we come to the end of our session. Once again, it was a pleasure to have you guys all today, and thank you so much, Chris. It was really, like very insightful, like breathtaking presentation, and like if like you're watching this I don't know, like later on from YouTube or something, you can also like reach out to Chris for anything you have about the matter, so feel free to. Once again, it was a pleasure to have you all guys today here with us.